Hello students, welcome to IIT PAL lecture series in mathematics. My name is Vetrivel. I am professor of mathematics at IIT Madras. I have been giving lectures on vectors now. This is my third lecture. In the first and second lectures we have seen how to represent a vector and what is the meaning of a position vector and how to find a section formula. How to represent a point that divides a given vector into a given ratio. And with that information we have written the equation for a line. So we call it vector equation of a line. Of course you are going to study the equation of line in your 3D geometry, but here we are going, that is maybe in the Cartesian form, but here we are going to see only in the vector form. So we call it vector equation of a line. So that is what you have learned so far. And in today's lecture we are going to see the important topic called the scalar products, the product of two vectors, and the resultant will be a scalar. And what is the meaning of that scalar, and what are the properties of these products, the scalar product, and using that we are going to derive some important identities and inequalities. Now let us start the topic now. So let us define the scalar product today of two given vectors. Take a vector A and let us say this is a vector A and this is vector B. What we mean by this, the scalar product of A and B, we generally denote it by the symbol A dot B. So it is also called the scalar product is also called dot product. Okay. And then this A dot B will give us a scalar. How to understand that scalar, okay, which is the resultant of this given vectors A and B. Okay. Now for that what I do is I just rewrite this. Let us take this vector A, and then now I just take the shift of this vector B, and let me call this angle theta that vector A makes with the vector B. Now obviously the theta lies between 0 and pi, okay, and we always choose the theta value. We choose theta between the 0 and pi. The scalar product is defined as, the colon equal, what we mean is defined by the length of the vector. So we will assume that A and B are non-zero vectors. If one of them is 0, then the scalar product will be 0. Mod A into mod B into cosine of that theta, the angle between the given vectors. Okay, so therefore we can choose theta between 0 and pi because of the cosine of the theta. Now this is the definition of the scalar product. So obviously k cos theta is a number between -1 and +1, and this is a positive numbers, okay, non-negative numbers. If one of them is 0, obviously it is 0, and else it is always, so the A dot B can be negative and it is a negative real number, or it can be a positive real number depending on the value of theta. Okay. If it is as long as it is acute, this will be positive. If it is greater than 90, then theta is greater than 90 degree, then it is A dot B will be a negative. So whenever A dot B is negative, you can immediately conclude that the vectors A and B are making obtuse angle. When A dot B is positive, then we can conclude that A and B are making acute angle between them. Okay. So this is the definition of the scalar product. And what does it mean, that we will see, and before that let us see some immediate properties. Number one property is A dot B whether we write first B or first A does not matter. So, what I mean to say is A dot B is same as B dot A. By looking at the definition you can just see, because it is a multiplication of 3 numbers, that is all. Therefore, A dot B is equal to B dot A. Number 2, if one of them is 0, A and B is 0, then A dot B is 0. Number 3, immediately we can go, if A dot B is 0, the converse is not true. Okay. If A dot B is 0, then we can that is if if theta equal to pi by 2, okay, if theta is 90 degree, then also A dot B is equal to 0, because cos 90 is 0. Therefore, whatever may be the lengths of A and B, the A dot B will be a 0. So, therefore, this is a number, okay. This is not a vector, A dot B is a number, and in this case, so therefore, if A and B are not 0, if we know that A and B are both are non-zero vectors, then what it means is A and B will be perpendicular, okay. If this is A and I can say this is B, then in that case the angle is theta is 90 degree, therefore, A dot B will be equal to 0. If A and B are non-zero, then A dot B 0, it is true that A and B are perpendicular. So, in this case A and B are, we say A and B are perpendicular. Let me, in short, let me write A is perpendicular to B vector. Okay. And now let me just to let, and there is one more thing, important property by looking at the definition. Suppose if B is equal to A, so let us see, if A dot A, what is it by definition? It is mod A, again mod A, that is square, and what is the angle between the same vector? It is 0, therefore, cos 0 is 1, therefore, simply it is A dot A will be A square. So, if A is a non-zero vector, this will be a positive number, and remember A dot A, therefore, A dot A, the vector A, and if I take the square root, then it is simply the length of the vector, okay. It is equal to the length of the vector A. So, if I want to find the length, immediately I can take the dot product and then take the square root, that gives the length has to be positive, therefore, we take the positive square root. So, that gives the length of the vector A. To illustrate this, let me take this simple example. If mod A is equal to 6 and mod B is equal to 7 and theta equal to 60 degree, then A dot B, okay, then A dot B is equal to, as I say, it is 6 into 7, because mod A into mod B into cos 60, cos 60 is 1 by 2, therefore, it is the answer is 21. Okay, so, what is 21? 21 is the scalar product of this given vectors A and B. And also note that what will be the I dot I, because we know I already in the previous lecture I have introduced I is the unit vector in the x axis, in the positive direction of the x axis. Okay. So, positive direction, this is I, this is j, this is k. I dot I is equal, because mod I is equal to 1, because it is a unit vector, mod I is equal to 1, therefore, it is simply cos 0 is 1, therefore, it is I dot I is 1. Similarly, j dot j is equal to 1, k dot k is equal to 1, and if I take the different vectors like I dot j, okay, because they are all perpendicular vectors, therefore, I dot j will become 0, j dot k becomes 0, and k dot I also becomes 0. And remember the k, j dot k. So, remember k dot I is same as the I dot k. So, because A dot B is equal to B dot A. So, I can write in whatever way you like, and next we see the some further properties of the dot product. So, next remark, now take two vectors A and B. Okay. So, let us say this is the vector A and this is the vector B, this angle is theta, okay. This is the vector B. Now, A dot B, let me consider the A dot B. A dot B is equal to, I can write mod B into mod A cos theta. Okay. And now, if I look at the projection, if I know this length is mod A and this is a right angle triangle, this making 90 degree here, therefore, cos theta is equal to, suppose if I call this point this M and then this, if I call this point let us say O, OM cos theta is equal to adjacent side by OM divided by the length mod A. Okay. So, with this mod A cos theta will be OM. Therefore, this length is equal to mod A cos theta. This length OM is equal to, that is, this implies OM is equal to mod A cos theta, that is the projection of the vector along the B. OM is equal to mod A cos theta. So, therefore, it is, if I look at this mod B times the projection, the length of the projection. Okay. This is not a OM is just, I am just denoting only the length, okay, this length OM. So, this is the length of the projection of A, the length of the projection of the vector A on the vector B. Okay. So, A dot B is simply the mod B times the length of the projection. So, therefore, it is, so A dot B, you can always say it is A dot B is equal to the length of B multiplied by, because this is a number, multiplied by the length of the projection of the vector, the projection of A on the vector B. Okay. So, this is the geometric meaning of the A dot B, and this vector, if I take A cos theta, that is mod A cos theta, the projection mod A cos theta, which is the length of the projection of A on B, and when if I multiply this with the unit vector in this direction, what is the unit vector in this direction? B by mod B. Okay. If I buy B by mod B, okay, then this quantity, that is, this is a number, a mod A into cos theta is a number, that I am multiplying by this vector B by mod B, which is a unit vector in the direction of B, then this, the whole thing becomes a vector. Okay. This whole thing becomes a vector. This vector is called projection vector, is called projection vector. If I denote only this is a projection, length of the projection. If I denote this vector, then vector is called projection vector, called the projection vector of A along B on the vector B. And so, this further some properties we will see, some more properties we will let us see one by one. If I take, so next remark, so maybe further properties. Number 1, A dot, because now we deal with more than 2 vectors. So, A dot B plus C, B and C are 2 vectors and there is another vector A. So, now A dot B plus C. So, I am taking the vector addition B and C and then I take the dot product. This is same as A dot B and then I take the sum of this A dot C. Okay. A dot B plus C is a number because I am taking this vector, I am taking the dot product. The left side is a number and the right side also is a number now. To understand this property, for convenience let me place the vectors like this. Let us say this is my vector A and this is my vector B. Okay. For convenience, this is my vector B and I place the vector C like this. So, this is A, this is B and this is a vector A and this is a vector C. Okay. Now, we know the B plus C is this triangle completion, this is my B plus C. Now, I am taking the projection. So, let me call this point A1 and let me take the projection of this big vector, let me call B1. Then the left hand side, now I am taking the left hand side A dot B plus C. So, A dot B plus C, A dot B plus C. By definition, it is equal to the length of A, length of the vector A, or simply length of A multiplied by the length of the projection. That is what we have seen, the dot product, the meaning of the dot product, length of A, length of the projection of B plus C on the vector A. Okay. Now, this is by definition it is equal to this is length of A means modulus of A and this is what is the length of the projection of B plus C, it is B1, okay, OB1, the length OB1, okay, the length, this is a scalar quantity OB1 and now OB1 can be written as OA1 plus A1B1, this is equal to mod A into multiplied by OA1 plus A1B1. Okay. This is equal to mod A to OA1 plus mod A A1B1. Okay. So, now if you look at OA1, this is the length of the projection of the B vector. Okay. So, this is equal to mod A multiplied by the length of the projection of B vector on A plus mod A times the projection of C, the length of the projection of C vector on A. So, this we can write mod A into mod B, this is nothing but by definition it is simply I can write A dot B. The first term is nothing but A dot B and the second term is nothing but the A dot C. Okay. So, therefore, this dot product satisfies the distributive property A dot B plus C is equal to A dot B plus A dot C. The same way we can prove the other properties. Let me just skip the proof, we can verify it. A plus B, there are 4 vectors now, I am taking the dot product with A plus B with C plus D. This is same as it is equal to, by definition it is A dot A dot C plus D plus B dot C plus D, and this we know already by the previous property. This is A dot C plus A dot D plus B dot C plus B dot D. It does not matter if we interchange A dot C with C dot A, it does not matter, both are same. And number 3, the modulus of A plus B. What is modulus of A plus B? It is equal to this, we can write A plus B by definition mod A square is equal to A dot A. Okay. Mod A is equal to square root of the A dot product A dot A. So, this is, therefore, it is A plus B dot product with the same vector A plus B, and this is equal to, now by the previous one, it is equal to, now this A and C are equal and B and D are equal, okay, the second property. So, because of that I can write this, this relation becomes mod A square plus mod B square, because B and D are equal, okay, plus 2 times A dot B, because A dot B is same as the B dot A, therefore, it is 2 times A dot B, and this is one property for this. And the next one, the fourth one, if I take A plus B, vectors A plus B dot product with the A minus B, it is simply, you can verify that it is simply mod A square minus mod B square, and the next property is A times A, the dot product of A with some k times B vector. What will be? By definition it will be, from the definition it follows that I can take the k outside, k times A dot B, okay, or it is also same as k A dot B. And one more property is A dot B minus C, A dot B minus C. By definition, by the previous properties we can write A dot B minus A dot C, and the another from the definition, the cos theta, because we know the definition of A dot B is equal to mod A mod B cos theta, therefore, cos theta is equal to, that is, if we know the dot product and the length of the vectors, then we can find the theta between them, the angle between the given vectors. So, cos theta is equal to A dot B, the numerator, and the denominator is mod A into mod B, provided none of them is 0 vector. So, in that case I can find the angle between the vectors A and B. So, that is theta is equal to, so this is same as A dot B divided by square root of A dot A square root of B dot B. So, we assume that none of the vectors A and B is 0 vector. Now, with this properties, let us find a simple formula, to find dot product, this dot product, scalar product, that is because we always represent a vector by the position vectors. So, in terms of if we introduce the coordinate system, we can, for example, if consider this vector. Let me just explain this in the two dimension with in the plane vectors, and then we can move on to the vectors in space. Consider the vector A which is equal to let us say A1I plus A2j, and vector B is B1I B2j. Then now I am taking the dot product A dot B is equal to A1I plus A2j dot product with the B1I plus B2j. Now this is equal to, by the property whatever we have seen in the previous set of properties, this is equal to simply A1I dot product with the B1I plus B2j plus A2j dot product with the B1I plus B2j. Again I am expanding this. This is simply giving, because remember I dot j we know it is equal to 0, I dot I is equal to 1, therefore it is simply we get only A1 B1. And similarly in this second term j dot I will become 0, because A2 B1 they are all scalars, only j and I are the vectors, therefore A2j dot B1I will become A. So this is A1 B1, so this will become 0, only the non-zero terms will be A2 B2. So the dot product between two vectors A and B is simply the component by the sum of the products of the components. Suppose the corresponding components I am multiplying A1 B1 A2 B2 and then we sum up. Okay. Similarly, if in general in the three dimensional vectors is given, for example in general if three vectors are given, let us say A1I A2j plus A3k and another vector let us say B1I plus B2j plus B3k, then the dot product, what will be the dot product? As we have seen in the 2 dimension, the same thing holds in the space. For corresponding components we multiply and then we add, that is A1 B1 plus A2 B2 plus A3 B3 for instance. So it is easy to find the dot product. Okay, we do not need to find the length of the vectors, simply A1 B1 plus A2 B2 plus A3 B3. Now to illustrate this, let me take this simple vectors. Let us take take A vector A to be 5I plus 3j minus 2k and B to be 8I minus 9j plus 6k. Now what will be A dot B? Is simply the sum of the products of the corresponding components. Okay. So this is simply 40 minus 27 minus 12, 5 into 8 and 9 into 3 and 6 into 2. So 40 minus 27 minus 2, 12 is equal to 1. So A dot B is equal to 1. And now I give one small exercise, you can do it yourself. Let us take A to be some vector, let us say 3I plus j plus 5k. Verify that mod A square, we know the mod A square, you know how to find mod A square is equal to A dot A. A dot A you know how to find, because A and B are here, A and B are same, okay, A dot A, and then you can find the right hand side and also you can find the left hand side. How do you find the length of the, you know the magnitude of any vector and then you can square it. So both are same, so you can verify this property of the dot product. And then before we go into the next ones, let us see some more problems based on the properties what we have seen. So for example, let us take A to be I by 2 plus j and B to be 2I minus j plus k. Prove that A and B are perpendicular. A is perpendicular to the vector B. Simply I can put this notation. A is perpendicular B. So what we do, we take the dot product A dot B is equal to the corresponding components, that is 1 2 into 1 by 2 and then minus 1, and here there is no k vector, that means the component of k is 0, therefore 1 into 0 is 0, therefore it is 0, therefore A and B are perpendicular. Now next the angle between two vectors, let us take my vector to be I minus j minus k and B to be, let us say 2i plus j plus 2k. Find the angle between them. So, what we do, the formula we know, cos theta is equal to A dot B divided by mod A into mod B. Remember this dot, the numerator, the dot is the scalar product and this is the ordinary product, the product between the scalars. Okay. So, mod A is a scalar, mod B is a scalar, this is ordinary product, this is a vector product, okay, that is scalar product, product between the vectors. And this is equal to A dot B is the numerator is 2 minus 1 minus 2 divided by square root of 3, and this is square root of the mod B is square root of 4 plus 4 plus 1, that is simply 9. Okay. So, therefore, it is equal to minus 1 divided by square root of 27. Since cos theta is negative, we can conclude that these vectors are making obtuse angle between them. And one more example, let us find a unit vector, let us take A to be this 2i minus j plus k, and take another vector B 3i plus 4j minus k. Now, we are interested in finding the unit vector, find unit vector, find the unit vector that is perpendicular to both, okay, perpendicular to both the vectors, both A and B. So, now let us take the vector, the new vector as let n, let us call the vector, the new vector as n vector, okay. And when the vector we want the n to be a unit vector. So, let us say initially this n is let us say xi plus yj plus zk. We want to know what the x, y, z are, and at the same time the n should be unit vector. What we have is this, it is given that our vector should be perpendicular to both A and B, therefore, A dot n should be equal to 0 and B dot n also should be equal to 0. Therefore, we have the immediately, since A dot n is 0 and B dot n also is 0, what we have is 2x minus y plus z equal to 0 is one equation, and the other dot product, that is B dot n, that is 3x plus 4y minus z equal to 0. So, from these equations, now two equations, three unknowns. So, we can solve by the Cramer's rule. So, x is proportional to, okay, the 1 minus 4, that is minus 3, and y is proportional to 5, that is 3 plus 2, and z is proportional to 8 plus 3, that is 11. So, x, y, z. So, if I call this lambda, then x is minus 3 lambda, okay, and y is 5 times lambda and z is 11 times lambda. So, what we want is a unit vector. So, now we have the n vector we know, and therefore, the required unit vector, how do we write? If I know the vector n, then simply mod it, that is a unit vector. So, here it is given by minus 3 I plus 5 j plus 11 k whole divided by the square root of, because this lambda, if I write x is equal to minus 3 lambda, y is equal to 5 lambda and z equal to 11 lambda, this lambda will get cancelled, okay, in the numerator and the denominator. It is simply 9 plus 25 plus 121. Therefore, this is the vector, this is the required unit vector. So, it is simply minus 3 I plus 5 j plus 11 k whole divided by square root of number 155. So, this is how we find the unit vector, that is perpendicular to given two vectors a and b. Now, let us find some application of this dot product. An application, work done by a force vector. Let us say that a force is acting at a point A, this is the point A, and a force is acting, let me call the vector F, and because of that force I assume that the A is displaced to another point, let us say B. So, the particle is moving from the point A to point B by the application of this force F. Okay. So, F is the force vector and AB is the displacement vector. And mod AB is the total displacement. And now automatically when the force is applied and when the particle moves from the point A to point B, there is a work done by the force. The work done by the force is equal to the force dot displacement, which you might have studied in physics, F dot the displacement, which is AB. Okay. For example, so if I know the force vector and the displacement vector, the dot product gives the work done by the force. To illustrate this, let me take this simple example. Assume that there are two forces. Okay, instead of one force, I have two forces are acting at a given point on a given particle. A particle acted on by two forces. Okay. So, I am just now the capital F is the resultant of two vectors F1 and F2, two force vectors, namely F1 2y plus j minus 3k, and there is another vector F2 is 3i minus 2j plus 2k. Then a particle is displaced. Okay, the particle is displaced from one point to another point. From, let us say, the point I am just I am having the position vector I plus from the point, that is 1 3 minus 1 to 4 minus 1 2. Find the work done by the forces. Find the work done by the forces. So, what we have to do is we have to find the, so the net force F is equal to the sum of these vectors. So, which is equal to 4I 3 plus 2 5I minus j minus k. So, this is the force vector, and the displacement vector is 3I, because I am 4I minus I minus j, that is minus 1 minus 3. So, and so on, that is 2 minus 1. Therefore, my D is 3I minus 4j plus 3k. So, I know the total force and the net force and the displacement vector. Therefore, work done, let me put WD, work done is equal to F dot D. If I take the dot product, we will get the work done, which is equal to, simply it is a number. Work done is the work is measured, it is a scalar quantity. So, it is F dot D is equal to 15 plus 4 minus 3, which is equal to 16 units. Okay. This is the work done by this force. So, we have seen some properties, the problems based on the properties we have seen, and finally, and one more I want to give an important identity. Okay, is a very important identity. Prove that is mod A plus B whole square plus A and B are two vectors, mod A minus B whole square. This is equal to, this is called the parallelogram identity, 2 times mod A square plus, because we know the parallelogram, if I know this is A, this is B, this is A, this is B, the diagonals are A plus B, and the other, this diagonal is A plus B and this diagonal is A minus B, already we have seen. Therefore, if I the sum of the squares of the lengths of the diagonal is equal to twice the sum of the squares of the sides of the parallelogram, mod B square. So, this is called a parallelogram law, and mod A plus, now this is easy to prove, because A plus B whole square, we know that A plus B whole square, from the dot product we can write this is simply A plus B dot A plus B. Is equal to square. So, by expanding this we get, already we have seen, this is equal to mod A square plus mod B square plus 2 times A dot B. Okay. Similarly, I can write A minus B square, this is equal to mod A square mod B square minus 2 times A dot B. So, therefore, if I sum it up, so therefore, our left hand side becomes simply mod A square 2 times mod A square plus 2 times mod B square. This is what we want to prove. So, which is equal to same as the our right hand side. So, this identity is very important and will be useful in many places. To illustrate this identity, let me give small example. Let us say mod A is equal to 3 and mod B equal to 4. If mod A plus B, if I know the mod A plus B, that is the sides of the parallelograms, 3 and 4, and if I know one diagonal a plus b is equal to 1, what is the other diagonal? That is mod, what is mod a minus b. So, simply we can use the previous identity. Therefore, by the above identity 1 by the above identity one plus mod a minus b, which we want to find, square is equal to twice 3 square plus 4 square, which is equal to 50. Okay. Therefore, mod a minus b is equal to 50 minus 1 49 and square root of that. Therefore, it is equal to mod a minus b, it has to be positive, therefore, we take the positive square root, which is equal to 7. So, this is how we find the other diagonal of the parallelogram. And I end this lecture with some important inequalities. Okay. Some inequalities. There are two inequalities. One is called Schwarz inequality, and other one is the triangle inequality. Because the Schwarz inequality is very simple. It is from the definition of the dot product. So, if I have a dot product between a and b, it is equal to modulus of a modulus of b into cos theta. Now, if I take and we know that the cos theta value lies between minus 1 and plus 1, therefore, if I take the modulus of that, this is simply less than or equal to mod a, because these are all positive value anyway, mod a into mod b, and the cos theta value is less than or mod cos theta is less than or equal to 1. Therefore, I just replace the equation by this inequality. Okay. So, therefore, this inequality is called the Schwarz inequality. So, always for any two vectors we have this modulus of a dot b is less than or equal to mod a into mod b. Okay. So, this is called the Schwarz inequality, okay, called the Schwarz inequality. And the next inequality is called the triangle inequality. It is again, that is if we have three places, let us say point A, point B, point C, going from A to C will be shorter than going from A to C via B. Okay. So, that is what is expressed in this inequality. Let us take two vectors A and B. I take the modulus of A plus B square, which is equal to, by definition of the dot from the definition of the dot product, it is equal to A plus B, the property of the dot product, A plus B. So, this I can write A dot A plus B plus B dot A plus B. Again, by simplifying, we get mod A square plus here also we have one mod B square, and we have A dot B, here B dot A. A dot B, B dot A both are same, therefore, twice A dot B. Okay. And this I can apply now the triangle, the Schwarz inequality for this term. The last term mod I am taking this will be less than or equal to mod A square mod B square plus 2 times mod A into mod B. and hence it is equal to modulus of A plus modulus of B whole square. Now, taking the square root both sides, what we have is A plus B always the shorter than, less than or equal to mod A, that is what I explained in this, mod A plus mod B. Okay, so, this is known as the triangle inequality. It is called the triangle inequality. Now, if when this equality will hold, okay, if equality holds in this, okay, if equality holds, what does it mean? That is, if modulus of A plus B is equal to modulus of A plus modulus of B, then what happens is from the this ACB, this B, mod AC is equal to, in this triangle what I have drawn, mod AC is equal to mod AB plus BC. Mod AC is equal to mod AB, the length mod AB plus mod BC. Okay. That is AC. If I take this triangle, the length AC is equal to the length AB plus length BC. That is what I have written here. What it means is simply ABC are lying on the same line. So, we say ABC are collinear points. They are collinear, the ABC, the points ABC are collinear. For instance, to illustrate this, what we have to prove? So, if we want to prove 3 points are collinear, simply we have to prove that the equality holds in the triangle inequality. I am sure you have learnt a great deal about the scalar product between two vectors, and we have seen the properties of the dot product. We have seen some important identities like parallelogram identity and the Schwarz inequality and the triangle inequality, and some more properties we have seen. And in the next class we will see the other product called the vector product. Unlike the scalar product, the vector product, the resultant will be a vector, and what does it mean geometrically, all that we will see in the next lecture. Thanks for watching.